Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Golang. And in the previous video, I finished with binary regression, binary logistics regression model. I had surprisingly a lot of the mistakes. I made a lot of the mistakes during the implementation, and in the previous video, I fixed them all. So right now, I have, for example, I have an example of training the binary model that predicts well two outputs like true or false, or is it something or it's not. And you can see that the output layer has only one neuron which can return two values, 0 and 1. And today I will continue next with the book, going to the chapter 17 already. And that is called regression. So let's start. Up until this point, we have been working with the classification models where we try to determine what is something. Basically, both models were trained on some data, and then we tried to predict the output class. For example, in the first version of the categorical the first model tried to predict, given the coordinates, it tried to predict in which of the three uh, models, in the three parts of the model, it predicts. In the second one, the last is binary logistics regression, it tried to predict if it fits into one data set or into another data set. But it could be anything. It could be, I don't know, cat versus non-cat or something like this. Now we're curious about determining a specific value based on the input. For example, you might want to use a neural network to predict what the temperature will be tomorrow, or what will be the price, what the price of the car should be. What will be the temperature tomorrow? Nobody knows, as usual. And you know, there are always predictions, but they far away from the truth. For a task like this, we need something with a much more granular output. This also means that we will require a new way to measure loss, as well as the new output layer activation function. It also means our data are different. We need training data that have target scalar value, not classes. So in the previous data, what we had is the output, the input was the coordinates and the output was the class. But here I can see that the input is probably a number and the output is a number. So linear equation. So first thing first, I need to implement this one. I hope that should not be that hard. Okay. Maybe here. Is in various programming languages. Interesting. They have Go. They have Go, but this one. No, I need the package. Where is it? This one? Yes. And I need the sign data. Where is it? Okay, so it's basically Okay, so it just calculates the scene value and returns it as really. Okay, so the x is hmm, okay, so -1, 1. I think it will return one-dimensional, well, a two-dimensional array with one thing inside. And let's just take a look. Not now. Or mm, test. Mhm. I need the numpy. Import num as p, right? And ah, print creates data, 100. And Python test. Okay. Yeah, I was right. I don't need to do this because I'm still going to implement it in a different way, but I'm going to create this. So right now we have this sign go, right? Um, what I need. Func, how I declare it, the previous one, scatter data, spiral data, vertical data. Okay, that will be sun data. And it takes number of samples. Samples in, and it returns tuple. And in that case, it will be too dense, actually. Yeah, I think it will be easier to make it in this way. Okay, so what do? We need to create a range from the samples. So, well, not the range. We need to iterate over sample counts. And okay, then we need to allocate two things. We have the X and we have Y, and then we have mad new dense one, no, samples one nil, and same and new dense, and same here, samples, wait, no, samples nil, one, maybe I should be consistent here and just return. Yeah, okay. I will return to what's called how the arrays are called in Go. Slices? Yes, two slices. Make so the type is float 64 and they have samples. And again, same float 64 and samples. So what we do, we assign I divided by samples, and yes, this should be plot return x, y, expected. Then we have y and just sign. Okay, 2 multiplied by math I multiplied by x value. That's it. Thinking, can I scatter this? Scatter. Okay, this one's scatter. Okay. I have x as float. I have y as float. Right. So I have float new in this one. Right. Plot. Okay. Then basically it's not an offset. Well, the offset is int. In my case, it's just len of x. Then again, len of x. I, it's easy. Color, okay. If error not, I'm not that good. And point, but that should be okay. No, let's try. First, I need to take the data from data set sign. Okay, 1000 could be good. Let's scatter sign data x and y. What it should do, it should create, right? Can I? How's it like this, right? And that's some shit. Doesn't look right, right? Okay. So then there is a question if it's the problem with the data or with, oh, yeah, there is, one small difference that I forgot to calculate the sinus value from it. Yes. Okay. That looks the same. By the way, can I increase the resolution? I think that's safe. Okay, I would go with 10. I think this is, small. Open sign. Yeah, much better. Okay. Okay, we have the data. We have the data. What's next? Linear activation. Since we are no longer using classification. Okay, and I think I can already. Maybe I should move these models into, well, actually, let's do this. I will do models. Oh, no, not here. That should be here, right? Then what I have binary, right? Package models. I, I will cut this one here. Imports main data sets. Import main layer. By the way, maybe I can, yes. Okay, we have the binary. Then the next one is, this is actually the categorical, the final version of categorical. No. Where's it's got to okay. Run model. I think I can remove this one. That's true. But what if I will, for example, model run binary model like this? Models. Okay, then I have this third one, and that will be what's called regression model, right? Regression. Models. Run. Models run. No. Okay, I think this is better. Since we are no longer using classification labels and want to predict a scalar value, we're going to use a linear activation function for the output layer. This linear function does not modify its input and passes it to the output. For the backward path, we already know the derivative of the single of the linear function is 1. Thus, the full class of our new linear activation function is, yeah. That should be in the activations, right? We have the rel activation. We have sigmoid. We have the softmax. Yes, the rel was the first one. Right now we have linear, right? Activation, what it should be. Type linear. How I called them before? Soft linear activation. Struct. And we have inputs, outputs, and the inputs. Okay. Inputs, maths, tens, outputs, and the inputs. Okay, then forward path. Linear activation. No. Forwards and takes inputs as math dense. Basically what it does. It stores the inputs and it actually takes the output and references the same one. Then we have the backward path, which is even easier. The values again, and I think the input should be equal to the values because we just take the actually we're making a copy. Okay, math dense copy of the values. That's it. It might raise the question, why do we even write some code that does nothing? We just pass inputs to outputs for the forward path and do the same with the gradients during the backward path. To apply the chain rule, we multiply the incoming gradients by the derivative, which is 1. We do this only for completeness and clarity to see the activation function of the output layer in the manual definition. From computational time point of view, this adds almost nothing to the processing time, at least not enough to noticeably impact the training times. Now we just need to figure out loss, mean squared error. Since we aren't working with classification labels anymore, we cannot calculate cross entropy. Instead, we need some new method. The two main methods for calculating error in regression are mean squared error and mean absolute error. With mean squared error, you square the difference between the predicted and true values of the single output and average those squared values. Okay, so we have the ground truth, we have the predicted, then we square it, then we make a sum, and we divide by the number of the outputs, where y means the target value, y hat means the predicted value, index I means the current sample, index j means the current output in this sample, and the j means the number of the outputs. The idea here is to penalize more harshly the further away we get from intended targets. Penalize more harshly the further away. Okay. So the more far away from the predicted, well, the more predicted values are far away from the ground truth, the more like more penalty those predictions get. Mean square error loss derivative. Partial derivative of the squared error with respect to predicted values. Okay. Okay, this I divided by j is a constant. We can move it outside of the derivative since we're calculating the derivative with respect to the given output j. The sum of one element equals to this element. With respect to the given outputs j, okay, so instead of the sum, we have the, well, I mean, that because we have many variables and we calculate not like with respect to all of them. We usually taking one particular one and we calculating the derivative against this one. I'm not sure if my explanation makes sense. Then we need to take the derivative, calculate the derivative from this. That will be 2 multiplied by this one. Yes, and then we multiply for the derivative from the value inside. The partial derivative of the subtraction equals subtraction of partial derivatives. Okay, this will convert into the value itself, and that will turn into the 1, right? Oh, yeah, this will turn into 0, yes. The partial, yeah, because partial derivative of the ground truth value with respect to the predicted values equals us since we treat other variables. Yeah, this is another variable. The partial derivative of the predicted value with respect to itself equals to 1, which presents this multiplied by the rest of the equation and forms the solution. Okay. I'm interested, why not just to put this minus inside? I mean, it will be the same. You just, change the, so it will be predicted minus target value multiplied by 2 divided by j. That's it. Okay. The partial derivative equals minus 2 multiplied by the subtraction of the true and the predicted values, and then divided by the number of the outputs to normalize the gradients, making their magnitude irrelevant to the number of the outputs. Mean square error loss code. The code for MSA includes an implementation of the equation to calculate the sample loss from the multiple outputs x minus 1 with the mean calculation was explained in the previous chapter in details in short words in the formula. For the backward path, we implemented the derivative equation which results in minus 2 multiplied by the difference of the true and predicted values and normalized by the number of the outputs. Similar to the other loss function implementation, we also normalize gradients by the number of the samples to make them irrelevant to the batch size or the number of the samples in general. Okay, let's implement this. What I need to do? Loss mean squared error. Okay, looking for the loss. Mean squared error loss. Okay. Type mean squared squared error loss. Okay. We will need D. Oh, it goes from the L to loss. From the loss, so I need the calculate. but I need the inputs. That's it. I need the inputs. So the inputs, math stands. Which one? For example, this one. Yes, I will need the calculate, which will be mean squared error loss. Yes, I will have this one. Then I have loss mean squared error forwards that takes predictions and the ground truth, which actually in this case is different, right? Because here we will have it as float 64. And then we'll have here prediction. Then, and we have target float 64. I will change targets, and here targets, and it returns float 64, right? And then I will have mean backward that takes d-values, again dense, and target to calculate, but no return values. So what I'm implementing, I need to return, well, actually the loss. Invalids. Oh, plot. No. No. Yes. And what is, I need to calculate the mean value. Mean value across rows. Okay, so we have the results, which will be make len of targets, right? And we return it. Then what I need to do, I need to go over RC equals to prediction teams. Then I'm going to right, and value, I will do this, but then for j equals to 0, j less than column, j is plus. Okay, what do we do? First, we need to value equal wait. By the way, here the math predictions should be this will output a scalar. The question is, will I have it as the rows or as the columns? But what I can do this. I can take the data from prediction data Then for item range data, right? And then what? No, wait. Why true? Well, it means that regression model, it should have, yes, it will have only one output, right? Right. But that's the point. So it means that I don't understand why I need the mean value. I mean, I will have only one. Well, maybe if I have the array. Okay. Also normalized gradient by the number of samples, but that's fine. I mean, again, well, this is the problem how to properly treat the. I will have the one array with the what's called the correct values for the x value. I will have basically, I think the input should be 1, 2. Okay. Okay, so again, I don't understand why we need to use mean here. Because forward should return an array. So I think in that case it will, just average. I mean, if it will be array of arrays and here it will be array of arrays, then it makes more sense. I mean, if we will have, for example, if I'm going to create a model that predicts several output values, then I will need to change it. But so far, I mean, okay, I will write this comment that predictions has one value for the sample. No, this is why target is single dim array. Otherwise, this code won't work. But what we can do? We can do. So the result equals to how of why true? Well, it doesn't actually matter the order because we set in it minus item second. That's it. Then we have the backward method. So, okay, sample count, output count against sample count, output count, but d values dims, then calculating the gradient. Well, first we need to number of outputs in every sample. We'll use the first sample to count them. Okay, so boom, boom, boom. Plus the inputs, I need to make then copy of the values, right? Then for loss the inputs apply func return 0 loss the inputs are we going to calculate it? There is -2 multiplied by target from the row minus minus d values at ing ing, okay, then divided by the output count and divided by the sample count, right? And that's it. Could expand. What do you mean? Could expand call to math. I mean, these things is a little bit fragile. I mean, they're probably I should stop, using the slices too and use the math dance everywhere so I can, for example, adopt this code for array. Well, for example, if I'm going to create a model that will try to predict several output numbers instead of one number, then I mean the mean value makes more sense here, and I will write it in a different way. But okay. The next thing is mean absolute error loss. And if I check the recording time, no. Okay, maybe I will check this and maybe stop for today, but let's see. With mean absolute error, you take the absolute difference between the predicted and true values in the single output and average those absolute values. So a little, more, it's not more kind of the same with squared. I mean, here you take the absolute value by getting rid of the sign. And in the previous one, we just squared the result that removed the sign too. But the magnitude of the values are different. Y means the target value, by hat means the predicted values, index I means the current sample, index J means the current output in the sample, and J means number of the outputs. This function used as a loss penalizes the error linearly, while in the squared one, and because of the square, powering into 2, it's the bigger error, the bigger it grows. So the penalty is higher. It produces sparse result and is robust to outliers, which can be both advantages and disadvantages. In reality, L1 loss is used less frequently than L2. Mean absolute error loss is used less frequently than mean squared error. So mean absolute loss derivative. The partial derivative of the absolute error with respect, so then we will have the basically the beginning is the same. The interesting part is this one, 1 and -1 based on the result. I already calculated the partial derivative of absolute value for the L1 regularization, which is similar to L1 loss. The derivative of an absolute value equals to 1 if the value is greater than 0, if it's or -1 if it's less than 0. The derivative doesn't exist for value of 0. Full solution. So the derivative for this function is this. It equals 1 divided by j. If this subtraction is greater than 0, it equals to -1 if this subtraction is less than 0. Okay, I think that's... there is an NP sign, and I think that's sign returns an element-wise indication of the sign. The sign function returns -1 if the provided value is less. Okay, if the x is equal and return. Okay, for the complex input sign function term, basically it takes the result of this expression, and then if it's a positive, then it returns 1. If it's a negative, it returns -1, and then we again normalize. Here, this is just takes the what's called absolute value instead of the square. So it's more or less, I mean, it's very similar to what we have here, right? So yeah, so this is mean absolute error, and then we're going to use it. Oh, there is accuracy in regression, and then regression model training, and there are some interesting things here. Oh, we'll have several layers. Nice. Okay. I will stop for today. I will start from the implementation of the mean absolute error loss code, so I can, recall all of the information that I learned today, and then I will continue with the accuracy and actual creation of the model from those layers, new activation function, and the new loss values. For now, thank you for watching, and I see you tomorrow. Bye bye.